Assalamualaikum dan selamat sejahtera. Welcome back to my channel, Physics from 5 SSM. Today I want to discuss Chapter 6, Nuclear Physics, on first topic 6.1, Radioactive Decay. So what is this, the word decay here? Radioactive decay is a random and spontaneous because it is not influenced by temperature, pressure and other physical factors. Because the process is random and spontaneous, we cannot detect which nucleus will decay first and what time the decay process will happen. That's why we call it random and spontaneous. The definition for radioactive decay is a process which unstable nucleus become more stable by emitting radioactive radiation. What is this radioactive radiation? So there are three types of radioactive radiation: alpha particle, beta particle, and gamma rays. Alpha, beta, gamma. Okay, I think you have studied this in lower form. Okay, what is this alpha? Alpha is nucleus of helium, He42. The nuclide notation. So you can see the nuclear number 4, proton number 2. Beta is electron. So the nuclide notation is 0, -1 e. Gamma is a wave or electromagnetic wave, so no nuclide notation, mass equals to 0. This is the symbol for gamma. For activity 6.1, you can go and search information regarding this alpha, beta and gamma. Okay, let's look at the radioactive decay process. There are three types of radioactive decay. The first one is alpha decay, beta decay and gamma decay. Alpha is a helium nucleus which consists of 2 protons and 2 neutrons. Let's say we have element X. The nuclear number is A, the proton number is Z, which nuclear number is equal to proton plus neutron. Okay, and Z is equals to proton number. So from here, if you want to calculate for neutron number, is N equals to A minus Z. So we get the neutron number. Okay. For alpha decay, it releases out alpha particle. You look at the general equation here. Let's say we have element X, nuclide notation is XAZ, release out one alpha. Alpha is 42He. So the new element that produces Y, thus the nuclear number for Y reduced by 4, the proton number reduced by 2. So actually balance number of nucleon, okay, left and right. Same thing, proton number left and right are balanced. So we have this one as general equation for alpha decay. Parent nucleus has proton number Z and nuclear number A. After alpha decay, the daughter nucleus has proton number Z minus 2 and nuclear number A minus 4. So if you look at the number of nucleon, if reduced by 4 and the proton reduced by 2 at the same time, meaning the decay process release out one alpha. Okay, so as example here, we have polonium to 1084, decay to become plumbum to 0682 and release out one alpha. If you balance the nuclear number left and right, we get here 210. The other side also is 210. Same thing, the proton number 84. Here also the total must be 84. Okay, so the parent nucleus decay to become daughter nucleus by releasing one alpha particle. Okay. The number of alpha particle actually depends on how many nuclear number and proton number change. Okay. For beta decay is the process where Okay, unstable nucleus decay to become more stable nucleus by emitting one electron or beta. Okay, so beta just now we already discussed as 0, -1e. Okay, so beta particles is a fast moving electron. During beta decay, a neutron in an unstable nucleus decomposes into one proton and one electron as shown below. What happens? Okay. The resulting proton remains in the nucleus while the electron is emitted with high kinetic energy as beta particle, as shown in figure. So you can see this is the general equation for beta decay. Let's say element X, nuclide notation is XAZ, decay to become new element Y. We check the nuclear number and proton number, no change in nuclear number, but you can see the proton number increased by 1. If this happens, means one beta is released out. Okay, so this is general equation. So if you check the number of nucleon left and right are balanced. So parent nucleus decay to become daughter nucleus and release out beta particle, okay, or electron. Okay. After beta decay, the proton number of daughter nucleus become Z plus 1, but nuclear number A does not change. So from here we know what type of decay that occur. Okay, remember no change in nuclear number, but the proton number increase by 1 means release 1 beta. As example here, natrium 2411 decay to become magnesium 24. The proton number increased by 1, thus release out 1 beta. For gamma decay here, gamma rays are high frequency electromagnetic wave. During gamma decay, an unstable nucleus releases its excessive energy to become more stable. Gamma rays have no mass and are neutral, no charge. No mass, no charge. Okay. For the general equation for gamma decay is as follows. You can see element XAZ decay to become the same element because no change in nuclear number and proton number and release out gamma. Gamma is in form of energy. Okay, so radioactive nucleus in excited state means decay to become nucleus which is more stable with less energy and then release out gamma ray. Okay. After gamma decay, there are no changes in proton number and nuclear number for the nucleus. The nucleus is less energetic after gamma decay. Example, cobalt 60 at high energy, release out gamma and become cobalt 60 also with less energy, which is more stable. Okay, one example, during the radioactive decay, some nuclei can emit more than one radiation. For example, during disintegration of uranium-234, its nucleus emits alpha particle and gamma ray. Yes, at the same time, sometimes alpha and beta can be emitted at the same time, called alpha and gamma. Okay, example of its decay equation and simpler decay equation as follows. For example, we have uranium-234-92 decay to become thorium-230. Okay, so this one release out one alpha and one gamma. Okay, so you can see the number of nucleon left and right are balanced. Proton number also balanced. So the simpler decay equation you can write as uranium 234 92 become thorium 23090 plus 1 alpha plus gamma. We can determine the number or the activity of the nucleus that already decay or not yet decay. So the time taken for the nucleus of the radioactive substance to become half is called half-life. Let's look at the definition. What is this half-life? When a sample of radioactive material decays, the number of parent nuclei which has not decayed decreases with time, while number of daughter nuclei increases. Let us do following activities to get an idea about half-life. The half-life, or T-half, is the time taken for a substance of radioactive nuclei to decay to half of its initial number. Okay, the keyword here is the time taken. The time taken for sample of the nuclei to decay to half. So we call it half-life. After one half-life, number of nuclei that not decayed will be half of its initial value. For example, if initial value is NO, after one half-life, it will become half from its initial value. Okay, so the time taken here, we call it half-life. When unstable radioactive nucleus decays, the new nucleus that form may also be unstable. The new nucleus will experience a series of continuous decay until a stable nucleus is formed. Okay, look at the figure 6.5 shows complete decay series from uranium-238 to lead-206 and their respective half-life. For example, you can look at here, uranium-238-92. The half-life is about 4.5 times 10 to the power 9 years. Okay, and then decay, release alpha to become thorium-234-90. Thorium has a half-life of 24.1 days. Release out beta to become protactinium-234-91. Okay, so you can look at the change in the nuclear number and proton number in order to know what type of decay that takes place. Either it's alpha, beta, or gamma. So you can just go through the schematic diagram here to show what happens to the nucleus whenever experience the decay process and also the half-life of each of the elements stated. Okay, so all the elements have its own half-life. Some are very, very long until millions of years, some very, very short, just a few minutes. Okay, so this one is depends on the material or the element. So you can see the final product which is stable is plumbum 20682. So you can look at how many decay process occur in order to become stable in the end. Just now, from the value of half-life, you can see uranium-238 is a radioactive element with a very long half-life, 500,000 million years. This element is trapped during the formation of rocks. The trapped uranium-238 will decay and eventually form a stable lead-206. This decay process takes a long time because decay rate is low. By determining the ratio of lead-206 to uranium-238 in a rock sample, age of the rock can be estimated. The higher the ratio, the older the rock. This geological method of measurement can be estimated the age of our Earth. Do you know the age of our Earth? Okay, so this one is can be used to determine age of rocks. For example, granite rock contains uranium isotope. Okay, and then uranium undergoes radioactive decay to form daughter nucleus lead. You can see a few uranium here not yet decayed, and some already decayed to become plumbum. How to determine the half-life of radioactive substance from its decay curve? Radioactive substance will experience random and spontaneous radioactive decay. The number of nuclei which has not disintegrated decreases with time. Difference Radioactive substances decay at different rates. The decay rates can be determined from decay curve. Let us carry out a radioactive decay simulation to draw a decay curve. Okay, example activity 6.3, you can carry it out here. To draw a decay curve, 10 plastic bags containing 60 dyes per bag. If you don't have dyes, you can use about 50 coins, like a 10-cent coin. Okay, so I have two faces, of course, head and tail. Okay, for the dice, you have 1, 2, 3, 4, 5, 6. There are 6 surfaces, but for coins, there are 2 surfaces. So the method is the same. Okay, throw the dice, 60 dice on top of table, or you just throw the 50 coins on the table. Remove all dice with display the number 3, record the number of dice left. Throw the remaining dice again on the table, remove the dice which display the number 3, record the number of dice left. So you do the same thing. Let's say you have coins, head and tail. Okay, what you do, you throw the 50 coins on the table, remove the coins that show head, and then record the number of the coins that show tail, mean the one that left. You can repeat the same throws until maybe you have about 5 throws. Okay. For example, I will show you this video. Okay. This one using coins. You can choose which face that you want to remove, which one you want to count as the one that left. So this one got 50 coins. Initially, before you throw, is 50 coins. Okay, now you throw, you just shake it or you throw on the table also can. What you do, you collect the one which, the one that show one face that you determined just now. Let's say the head. You remove the head, and then you count the tail that left, and then you record for the first row. Let's say 26. Okay. And then the second row again. Okay, you record the one that left in the table. You repeat the same things until you have recorded everything and no more left. This one how many times? 10 times, 10 throws. Actually, you can stop at 5 throws already. Now you can plot a graph number of coins left against throws, number of throws. Okay. So you can see the curve that you produce. You can just draw the curve. Initial is 50. So it's a curve graph. It will never cut the x-axis. So actually, by throwing the coins and then you collect the one that the face that you want, actually this one is just like probability activity. Probability of getting hit. So you can see this one, you can determine from 50 to become half, 25. So the throws there stayed as 1. So if this one represent time, okay, the x-axis represent time, meaning that time taken, we call it half-life. Okay. So you can do the same thing, the same method in order to get this curve graph, or known as decay curve. So we can have analog situation as a nucleus of element that decay. Okay, after one throw, the one that decay is equals to 24, not yet decay 26. Okay, after two throws, it becomes 15, meaning not yet decay 15, already decay is 35, something like that. Okay, so this is the nucleus of radioactive material. Also the same, the molecules or the nucleus also experience probability, means they have same probability to decay. Okay, because it is a spontaneous and random uh, process, so we cannot detect which one will decay first. Okay, okay, so the concept of half-life can also express in the form of decay series as follows. Okay, initial value or number of nucleus, also can number of radioactive nuclide or activity. After one half-life, it becomes n divided by 2. Become the second half-life, it becomes half of the previous one. So half from NO over 2, it becomes NO over 4. After another one half-life, it becomes NO divided by 8, and so on. So what we can say about the number of radioactive nuclei that not yet decay n is equals to half to the power n NO, where NO is initial number of radioactive nuclei, N is number of half-life limited to positive integers, and T half is half-life of radioactive substance. If we look at carefully how we get this formula, how we get that, okay? Just now we already showed that after one half-life, the fraction that left means not yet decay. One half-life, it becomes half of NO, means not yet decay is half. After two half-life, it becomes NO over 4, meaning here is the fraction left is 1 over 4. After three half-life, it becomes 1 over 8. After four half-life, the fraction left is 1 over 16. After five half-life is 1 over 32. If you look at carefully, 1 over 4 is half to the power 2. 1 over 8 is half to the power 3. 1 over 16 is half to the power 4. 1 over 32 is half to the power 5. And this one half is half to the power 1. So you can look at here, n equals to 1, the power here is 1. N equals to 2, the power here is 2. N equals to 3, the power here is 3. And power 4, power here is 4. N equals to 5, power here is 5. Thus, we can make a general assumption that if n half-life, thus the fraction left will be half to the power n. If the fraction left is half to the power n, thus activity left n is equals to the fraction left multiply initial activity or initial number of radioactive nuclei. Okay, so this is how we get that relationship. Okay, so actually this one can be used to solve problems involving half-life. This one is the activity which is not yet decay. When we talk about fraction left means not yet decay. Okay. If you look at the table here, you can see. Okay. Initial condition, number of decayed nuclei 0. Okay. This one is not yet decay, has not yet decay. So after one half-life is half NO and so on. Not yet decay, the fraction you just take 1 minus the fraction left. So for this one, the one that left for one half-life is half. So means the decay one is 1 minus half. So it becomes half. Okay. Second half-life, 1/4. This is not yet decay. So the one that already decay is 1 minus 1 minus 1/4. So you get 3/4. Okay. For 3 half-life, 1/8 does already decay is 1 minus 1/8, 7/8. Okay. And finally, 5, you can see 1 minus 1/32 is 31/32. So you can see the number of nucleus, okay, become half every half-life. Okay, so you can see here become half. This one half from here, this one half from this one half from this one, and this one half from this one. We have another one. The one that left here is 1. The next half-life, and so on. Okay. Okay, from the decay curve, okay, the shorter the half-life of the radioactive sample, the higher the rate of decay. Okay, if you look at here, this one is longer half-life. Okay, this is the graph. Okay, decay curve. So you can determine from here, NO become NO/2 is here. So you just can read the value of T here. So this is half-life. If you compare two materials or two elements here, the one with short half-life will have higher decay rate. So you can see the graph is more curved. The one with longer half-life is lower decay rate, meaning number of nucleus that decay is smaller compared to the one with shorter half-life. The short one can change to other element faster compared to the one which is longer half-life. Okay. Okay, let's look at solving problem involving half-life. Let's say example 1, we have a radioactive material stored in the lab, has initial activity 480 seconds to the power -1, half-life 6 minutes. How much activity in 60 minutes? Okay, there are more than one method to solve this one. I'm going to use this method, the one that we discussed before. This one. Okay. Information given, NO equals to 480 seconds to the power -1. And the half-life equals to 6 minutes. Given time is 30 minutes. How much activity? Meaning we need to find what is N. Okay. So for the time taken 30 minutes, how many half-life, okay, that the substance or the radioactive material pass through to become a certain value of activity. So we can determine the number of half-life, which is N equals to T divided by half-life. So it means 30 divided by 6 equals to 5. 5 half-life. Okay. Thus, the activity left N equals to half to the power 5 times initial activity 480. So what we get here equals to 15 seconds to the power negative 1. Okay. Second example, radioactive material stored in the lab has half-life of 10 days. T half 10 days. Calculate number of days taken for activity to reduce to 25%. Okay. One method is by using schematic diagram like this. So you can see mentioned in percent, this initial activity is 100%. Okay. After one half-life, which is 10 days, it becomes 50%. After another one half-life, it becomes 25%. So how many half-life already? 1, 2. So the time taken equals to 2 half-life. Thus, the number of days required is 2 times half-life, 10 days, so 20 days. Okay, therefore, activity of the remaining radioactive material become 25% from its initial activity in 20 days, okay, or after 20 days. Okay. If you want to determine using the formula just now, n equals to half n and o also can. So from here, what you do, you determine the fraction left equals to 25 over 100, 1 over 4. 1 over 4 equals to half to the power 2. So you get 2 here means 2 half-life. So the time taken is 2 half-life. 2 times 10, 20 days. So the same answer, same answer. Example 3. The ratio of argon 40 to potassium 40 sample volcanic rocks is 3 to 1. In early formation of rocks, there was no argon element trapped in it. If potassium 40 decays to argon 40, half-life 1250 million years, estimate age of rock. Okay, now the information given. Okay, for one half-life, the ratio of the fraction, the one that left and the one that decay. So actually the one that decay become argon 40. So this is not yet decay. This is the decay one. The decayed one actually changed to argon 40. So the fraction of the argon 40 will become 1 minus half. So we get half. So the ratio will become half to half, thus become 1 to 1. And then after 2 half-life, the has not decayed one is equals to 1 over 4. The one that already decayed is 3 over 4. Because 1 minus 1 over 4, so get 3 over 4. So the ratio will become 3 over 4 to 1 over 4. Because this one we want the argon 40 to potassium 40. So here we can simplify, we get 3 to 1. Okay. So now we get what we want here. The ratio is 3 to 1. So the time taken is 2 half-life in order to ratio to become 3 to 1. So 1 half-life is 1250 million years. So age of rock is equals to 2 half-life. So 2 times 1250 million years. So we get the age of the rock 2500 million years. Okay, next you can try Formative Practice 6.1. You can try first, and you can come and check the answer. Let's look at the number 1. Complete the radioactive decay equation. Identify A, B, C. So what is A here? Release 1 beta. So for the new element that produce, the nuclear number still the same. Okay, the proton number increased by 1, 89. So you can check what is the element with nuclear number 22889. Okay, B, polonium 20984. Okay, you can see the nuclear number reduced by 4. The proton number decreased by 2. So what is this B? So for the B, the nuclear number equals to 209 minus 205, which is 4. For the proton number, 84 minus 82 equals to 2. Thus, B is equals to element with nuclear number 4 and proton number 2. That one is nucleus of helium or alpha. Thus, B. Alpha. Okay. And then C. What is nuclear number for C? Is equals to 1 plus 0 equals to 1. Proton number equals to 1 minus 1, which is 0. Thus, C is neutron. Okay, nuclear number 1, proton number 0. Then number 2, decay series of radioactive source is uranium-23892 become 20682 plumbum. Determine the number of alpha particle and beta particle emitted. Okay, so we want to determine alpha and beta. So you can just write generally the equation. Plus, we don't know how many alpha, you just can put X of nucleus helium and Y of electron. So this one just mathematical operation. So the number of nucleon left and right must be balanced. Thus 238 equals to 206 plus X times 4 for X plus Y times 0 is 0. Thus we get 4X equals to 52 and X equals to 8. Okay, so we have 8 alpha. And then 92, the proton number equals to 82 plus 2 times X to X, Y times -1 minus Y. We substitute X equals to 8. So you will get Y equals to 98 minus 92, which is 6. Okay, so we get 6. So there are 8 alpha and 6 beta. Okay, number 9, table shows record of activity of radioactive samples stored in the lab. Determine half-life of the radioactive sample. You can use the method of a schematic diagram, or you can use method by calculation the fraction left to determine the half-life. Okay, for example, I choose this one from 10 January, 20 January. So the fraction left here is 380 divided by 1520 is equals to 1 over 4, which is equals to half to the power 2. So from here we get, okay, from 10 January to 20 January actually equals to 2 half-life. Thus, 2 half-life equals to 10 days. So we get half-life equals to 10 divided by 2, 5 days. Okay. A sketch radioactive decay curve for the sample. Can look at this one. The y-axis is activity. The x-axis is time, which is in days. Okay, initial one, 1520, become half, meaning 760. Half of this one is 380. Okay, so initial one is here. Let's say here is 5, 10, 15, 20. Okay, one half-life is 5 days. So 150 become half, the time taken is 5 days. And then from 760 become half, one half, another one half-life is 380. 380, half of it is 190. Okay, half of 190 is 95. So it should be here. So now we can just draw a curve. Okay, so you will get the decay curve like this. Okay. Okay, so that's all our class today. Okay, thank you for watching. Bye.